This video will discuss MGSE 9 through 12 FBF1A, determine an explicit expression and the recursive process or steps for calculation from context. In the high school curriculum, students will have multiple opportunities to investigate this standard, as they will address it in their study of linear, quadratic, and exponential functions. Students are first introduced to the term function in 8th grade, but they begin to gain experience with functions in elementary school. In kindergarten, students use patterns with numbers, such as the 5 plus n pattern, to learn particular additions and subtractions. In 4th and 5th grade, students work with these patterns in which a rule is explicitly given. These pattern standards from 4th and 5th grade expand to the domain of ratios and proportional reasoning in 6th and 7th grade, where in 6th grade students work with equivalent ratios, tables, and graphs, and the relationships between them, and in 7th grade, students recognize the multiplicative relationship when identifying the constant of proportionality in equations. As stated earlier, students are introduced to the notion of functions in 8th grade, the major focus being the study of linear functions, but they also discuss and provide examples of nonlinear functions. In high school, students build upon their work with functions in grades K through 8 and deepen their understanding of linear functions while expanding their work with functions to include quadratic and exponential functions. These students are recreating this pattern from GeorgiaStandards.Org. GeorgiaStandards.Org is a free resource which provides teachers with various patterns, including linear, quadratic, and exponential patterns that can be used when addressing standard FBF1A. Using visual patterns such as these allows students to make concrete connections between a visible pattern, which can be described recursively, and the explicit expression that describes the recursive process as asked for in this standard. As you will see, these students are using concrete materials to recreate the given pattern and using the concrete model to determine the recursive process which describes the pattern.
You notice any patterns so far?
Yeah, they all the blues increase by 1 on the column and on the row.
So they increase by 1 on the column and on the row. So all together, how much does it? So let's say if I refer to this as stage 1, and this one's stage 2, stage 3, and you just created stage 4. As you go from stage to stage, how would you say that it changes?
So as you increase the number of the number of blue blocks, the larger the L is.
Okay, so as the blue blocks increase, the larger the L is. What stays the same from stage to stage?
The red.
The one red stays the
In the
same
corner.
in the corner there. And so then the change is, so here's one blue, there's one blue, so how much do you think it changes each time?
Twice.
With 2? Okay. So let's see if that works. As I go from stage 1 to stage 2, did we add 2 more blue blocks?
Yes.
And then from 2 to 3?
Yes.
And then 3 to 4?
Yeah.
Yes.
By using the concrete materials to build the pattern, students are able to physically see the constant quantity, which is the red tile within this pattern. Students are then asked to enter the information into an XY table, with X representing the step or stage and Y representing the total number of tiles within each step or stage. Students will then be able to look for the relationship between X and Y and describe the relationship with an explicit equation.
Yeah, it looks weird
Why does it look weird?
because before we had a pattern of 2, 4, 6, 8, and it was counting by 2s. Now I don't think there is a pattern.
So from 3 to 5, how does it change?
That's adding 2.
Okay.
Oh wait, there is. You're still adding 2 as you increase. So then this would be 11 because there's another pattern.
Does that make
Of adding
sense?
2. Yes.
Okay, so now let's look at the relationship between X and Y. What do you think has to happen to X in order for it to be equivalent to Y?
You have to add 2 to X in order to get Y. So for example, well no, because I mean it works for number 1. 1 plus 2 is 3. 2 plus 2 is 4 though. And that wouldn't work for our second one.
What do we need to do to 2 to make it 3?
Wait, we can do 1 times 2 then plus 3. not plus 3, plus 1, and that could get us 3.
Does that work for the second one?
2 times 2 is 4, plus 1 is 5. Yes!
Yes.
Ooh,
That works.
that makes sense.
Okay, so
So then now let's think about what is happening to x then to help us write our equation.
okay. So what's happening to x is
What's the first thing that you did to the x values?
I multiplied
You're
them by 2.
multiplying the x value by the number of blue blocks that's increasing from
Yes.
stage to stage.
Nice. And then what did we do after that?
Added 1,
Add 1 for, and what's representing that plus 1?
the constant red.
That constant red. So what do you think the equation will look like?
X times 2 plus, I think so.
Students were next presented with this different linear pattern from visualpatterns.org, and not only were they asked to determine stage 5 of this pattern, but they were also asked to work backwards and determine stage 0 and stage -1. In the following clips, students explain the recursive process they use to obtain these stages of this pattern.
So for stage 5, I just added 1 more to the top, 2 more to the sides, and then for stage 0, I had to subtract 1 from the top and from the sides. And stage -1, instead of going up, I went down.
And yours?
So for stage -1, I put the same thing as stage 1, but to represent negative, I put y in each boxes. And then for stage 5, I did what Joy did. I put 1 on the top, add 1 on the top, and add 2 on the bottom.
So tell me his idea then.
Of how, since for this one we add 1 up here and add 2 here, then we could take away 2 on, we could take away 1 on these sides and take away 1 there, and we'll just have 1
So what stage would this be?
of stage 0.
That's stage 0?
Yeah.
That's stage 1.
Oh, well, whatever you say.
So then what would stage
Okay.
0 look like then?
So I noticed that we add 1 on the top and 2 on the sides. So we'll take away 1 off the top and we'll take away 2 off the sides, and that'll be stage 0.
Interesting. Why did you have that one blue? You don't
Oh,
know?
because I
Okay.
had did it saying that would be the last one, the only one left.
That would be the only one left. So then if we use Jaden's idea, can you put it back together real quick? If we use Jaden's idea of taking 1 off the top, as he said, and then 2 off the sides, what is the one that's left?
The blue one.
The blue one. So what would that look like?
Like that.
And what stage would that be?
0.
Stage 0.
Visual patterns can also be used to assist students as they begin their investigation into quadratic functions and exponential functions. Here are 2 more patterns from visualpatterns.org. How do you see each pattern growing? What is the recursive process for each? Can you determine an explicit equation for each of these 2 patterns? Pause the video and discuss each pattern with your colleagues. The site UCubed is another free resource that is worth checking out. Among its many resources, this site provides tasks which allow students to visually explore and describe different types of functions. The tasks are open, visual, and creative, and they integrate brain science, mindset, and other important messages to students. For more information on the resources available through UCubed, please visit their site at the link provided in the listing of resources for this video.